Welcome to our next lecture in Chapter 4, 4.2, Least Squares Regression. Here we're going to find the least squares regression line and use the line to make predictions. Interpret the slope and the y-intercept of the least squares regression line and compute the sum of squared residuals. Table 5 represents the club head speed and the distance a golf ball travels for 8 swings of the club. We found that these data are linearly related earlier. A, find a linear equation that relates club head speed, x, the explanatory variable, and distance, y, the response variable, by selecting 2 points and finding the equation of the line containing the points. B, graph the line on a scatter diagram. C, use the equation to predict the distance a golf ball will travel if the club head speed is 104 miles per hour. Normally the lowest and highest are the points that we pick, generally from 2 points. Normally we pick 2 points, obviously to create a line, and normally we pick the highest and lowest. Here we picked 99, 258. That's the x and the y value from the table, the lowest value, and 105, 275, x and y, x being 105, y being 275, because a line drawn through these 2 points seems to give a good fit based on the scatter diagram shown in the figure. And there are 2 distances at 105, so we are picking a high point and the low point. To find the slope and the equation of a line, we just use those 2 x and y values to find the slope, which gives us 2.8. And then we pick the slope in one of those points and plug it into the point slope formula here, and we get down to the y equals 2.833x minus 22.49, etc. And this is the slope-intercept formula. Okay, this is the equation of a line in the slope-intercept formula. So now we have an equation for a line based upon the explanatory variable x. Here we've drawn the diagram. This is the same one you saw before, where we've drawn the line between those 2 points. To predict the speed at 104, we simply use the linear equation where x equals 104, plug that value in, and then find out. And so here we get a predicted value of 272.2 yards. So what this does is, if our data is in a linear format, we can create an equation of a line that then allows us to predict other values that weren't observed. Perhaps a lot of times it's future values. This case it was distance and time. Values before, intermediate values, what we saw here. But this is really a predictor of other values. And this is often how we use statistics so that we can make inferences about what would happen in other cases. So we predict here that a golf ball will travel 272.2 yards when it is hit with a club head speed of 104 miles per hour. Find the least squares regression line and use the line to make predictions. The difference between the observed value of y and the predicted value of y is the error, also known as the residual. Okay, the residual. So the residual equals the observed y minus the predicted y. Okay, so here we can see that y equals 274 minus 269.3, which is approximately 4.7 yards. The residual for a club speed of 103 miles per hour is presented in the figure by the length of the vertical line segment drawn between the points 103, 269.3, which is the predicted line, and 103, 274, which was the actual observed. And so that's how we get this here. If we plugged in 103 back into our linear equation, we would get this, and then we have this from our table of observed values. The least squares regression line is the line called y hat. You can see that with a little, looks like the exponential sign above the y. The least squares regression line is the line that minimizes the sum of the squared errors or residuals. We represent this as minimize the summation of residuals squared. This line minimizes the sum of the squared vertical distance between the observed values of y and those predicted by line y hat. The equation of the least squares regression line is given by y hat equals b sub 1x plus b sub 0. The slope b sub 1 is equal to r times sy over sx, right? This is the standard deviation of the sample for y over the standard deviation for the x variable. The y-intercept, b sub 0, equals the sample means for the y variable minus b sub 1, which we just figured out is the slope, times the sample means for the x variable, the explanatory variable. These formulas are important, so you need to have those down in your notes. Find the least squares regression line by hand. Find the least squares regression line for data in Table 2. And I've given you all the formulas down there in the bottom on the right, which should also be in your note. In the previous example, we found that r equals negative 0.946. The sample mean for x is 4. The standard deviation for x is 2.449. The sample mean for y is 10, and the standard deviation for y is 5.61. So remember, B1, this is the slope, equals r times the y standard deviation over the x standard deviation. So we plug in those values and we get negative 2.1676. Now we're able to write the equation b sub 0. We're able to solve for b sub 0 now, which is equal to the sample mean of the y variable minus b sub 1 times the sample mean of the x variable. Plugging in those values, we get 10 minus negative 2.1676 times 4, which gives us 18.6704 for b sub 0. And now we can plug those into the equation y hat equals b1x plus b sub 0, and we get our equation for the line. We get our least squares regression line, or what we know as y hat. Y hat is an estimate of the mean value of the response variable for a particular variable of the particular value of the explanatory variable. It is an estimate of the value of the response variable for a particular value of the explanatory variable. So let's look at the same example, but this time instead of calculating it by hand, let's use some technology. And so here you actually see 4 different technology results. I know that they're not very easy to see, but you can also look at these in your book. But here we have the TI 84 Plus. Here we have Minitab. In the second diagram below, C is actually from Excel. And then D here is from StatCrunch. And there are videos in your learning section that will help you figure out how to use each of those technologies to find the least squares regression line. So that was our first part, was to find the least squares regression line in each of these. And you can see the values highlighted that we use to input into the equation. Okay. Our next step is just to draw the least squares regression line on the scatter diagram of the data. And here you see the scattered diagram with all the points here that we actually observed, and then we have the least squares regression line. This was done using StatCrunch. Next, we want to predict the mean distance the golf ball will travel when hit with a club speed of 103 miles per hour. So we did this by hand. We're going to do the exact same thing, plugging this value in. So this is a calculation. Even though we use technology, we're still going to use the results from the technology, which were these two B0 and B1 factors, and then plug it in. And so we get the same answer, 270.3 yards. Notice that in D, we're trying to predict the distance of a particular golf ball will hit, etc. And so here we do the same thing, actually, whether we're trying to predict the average distance or the actual distance or the distance of a particular ball. We use the same formula. Because we don't have an average of these values, that's why we use the same formula for either a average distance at a specific input value or explanatory variable value, or for a particular observation. Finally, determine the residual for the predicted value found in part C. Is the distance in table 5 above average or below average among all balls hit with a swing speed of 103 miles per hour? So remember, our residual is the observed value, response variable, minus the predicted value. The predicted value was 170 or 270.3. From the data in table 1 from before, the observed distance when the swing speed is 103 was 274. So we get a residual of 3.7 yards. Because this number is positive, this means it is above average. And you can see that here. It's above average. It's above the mean that's predicted. Okay? Our next objective is to interpret the slope and the y-intercept of the least squares regression line. In algebra, we learned that the definition of slope is rise over run, or the change in y's over the change in x's. If, for example, if slope equals 2/3, positive 2/3, then as x increases by 3, the denominator, the y will increase by 2. So as x goes up, y will go up. If, however, the slope is negative 2/3, then as x increases by 3, y will decrease by 2. So as x increases, y decreases, and we have the opposite effect, a decreasing function. Statistic models, such as the least squares regression equation, are probabilistic. This means that any predictions or interpretations made as a result of the model are actually based on uncertainty. They're just predictions. They're not fact. They're looking at trends. Therefore, when we interpret the slope of a least squares regression equation, we don't want to imply that there's 100% certainty behind that interpretation. This is a prediction, not an actual calculation. So when we look back at our regression line equation that you see here in the yellow up top, the two interpretation of slope for this regression line are acceptable. And here's the slope. Remember, it's the number in front of the x, since we have a linear equation in slope intercept form. If a club speed increases by 1 mile, if you think about putting this integer value or this numerical value over 1, as the club speed increases by 1 mile per hour, the x value or the explanatory value, the distance the golf ball travels increases by 3.1661 yards on average. That's the mean. Remember, the two interpretations are the mean and the actual. The other interpretation, if club speed increases by 1 mile per hour, the expected distance the golf ball will travel increases by 3.1661 yards. Again, we're looking at two interpretations. One is on the mean or the average, and the other is on an actual observation or an expected observation. We also have interpretations of the y-intercept. Okay, the y-intercept is this number out here, b sub 0, from our formula. The mean of the y variable minus b1 times the mean of the x variable, the explanatory variable. The y-intercept of any line is the point where the graph intersects the vertical axis or the y-axis. We find this because everywhere along the y-axis x is equal to 0, so we set x equal to 0 in the equation and solve, and we get this value here. In general, we interpret a y-intercept as the value of the response variable when the value of the explanatory variable is 0. Okay, the response variable when the value of the explanatory variable is 0. So because of this, we first have to ask two questions. Is 0 a reasonable value for the explanatory variable? When you think contextually about what the explanatory variable is it possible to reach a value of 0 in whatever you're observing? And second, are there actually any observations near that variable equaling 0? Did you take any observations that were close to a 0 value for that explanatory variable? If the answer to either question is no, then we do not interpret the y-intercept. In our regression equation, the y variable is swing speed, and it makes no sense to think about swing speed. And if we plug that in as 0, then we see that the distance that the ball will travel is negative 55. So it doesn't make any sense at all. So in this case, we're not going to interpret the y-intercept, because a club speed of 0, it means the club's not moving, which means you can't hit the ball, which means you certainly aren't going to have any distance from the effect of the club speed, or the swing speed. And if we plug that in, the value we get makes even less sense as well. The second condition, remember, is do we have any observations near 0, near the explanatory variable equaling 0? This is especially important because we should not use a regression model to make predictions that are outside the scope of the model. Okay, now pay attention to that. You don't want to use a model, you don't want to use the regression model to make predictions outside the scope of the model. So again, if we're talking about the club swing speed, to take this to make it farcical, imagine the club speed swing was 1,000 miles per hour. Well, I don't think that's humanly possible for someone to swing their club at 1,000 miles per hour. And I mean, I'm taking it a bit extreme to kind of make the point here that if we don't have any values near 0, it's likely that those values don't make a lot of sense. What this is meaning is we should not use the regression model to make prediction for values of the explanatory variable that are much larger or much smaller than those observed. We should not use the line in the previous example to predict distance when club head speed is 140 miles per hour, because the highest observed club head speed is 105 miles per hour. The linear relation between distance and club head speed might not continue. And they're just showing some possible reactions here. So again, there's two conditions for interpreting the y-intercept. Does a 0 for the explanatory variable make sense? And are there values that we observed that are near 0 on the x-axis? Our third objective is to compute the sum of squared residuals. Compare the sum of squared residuals for the lines in the two previous examples concerning the club head speed and the distance the ball travels. In the first example, we just made a linear regression. That is means we picked the smallest value and one of the higher values at 105 to draw a line between those 2 points to kind of make a linear estimate, on a linear equation that we could use for estimating. Okay. In example 3, this is a similar process, except we use the least squares regression line. Okay. And so that's what you see here. And so we've calculated the residuals and then the sum of the residuals squared here and here. Okay. I'm not going to walk through all of these, but table 6 contains the value of the explanatory variable in column 1. In column 2, it's the corresponding response variable. Column 3 is contains the predicted values using the linear equation we created in the first example. Okay. We then computed the residuals, the observed, the data we actually had, minus the linear prediction. Okay. Column 5 contains the square of those residuals, and column 6 uses the least squares regression. This is the second of the examples. This is a different linear equation, as you can see, using the least squares regression equation that we just learned about and have gone through several examples. Recall that by definition, the least square regression line minimizes the sum of square residuals. Okay, so what you can see here is the sum of the squared residuals for the linear regression we did just on paper is 56.91. The sum of the squared residuals for the least squares regression is 49.46, which is what we expect, because any other line that we use to do predictions or look at trends to see, to use a linear model to predict other values, will have a sum of squared residuals greater than our least squares regression. And we do that by definition so that we have kind of a more conservative linear model when making predictions. Okay, we do hear that again. We do that to create a conservative model for linear models for making predictions. Okay, and so here you can see the two lines. You can see the regression line above, and then just the linear regression that we did. The least squares regression is above, and the linear, and this is just so you kind of get a visual of that. Okay, get a visual of that.